Oh yeah, it's day. Hello guys. So welcome back. And today we're going to tackle a question on design of engineering structures. This one here was part of a question on the CDACC March-April series. So once again, I hope you're going to learn something. Let's delve straight into it. So the question reads, a 400 millimeter square column carries a dead load of 1050 kilonewtons and an imposed load of 300 kilonewtons. The self-bearing capacity of soil is 170 kilonewton per meter squared, already given. Then design a square pad footing to resist the loads, assuming the following material strength. We have characteristic strength of concrete as 35 Newton per millimeter square. We have yield strength of steel as 500 newtons per millimeter square. So we also have a sketch of the load path, or maybe how the load is transferred from the column to the footing, like so. So as usual, we are going to use our golden rules or our design principles to work this question out. So which is to work on the demand side. We are going to work on the demand side or the load side. The demand side or the load side, which represents the loads that are trying to break or bend or crash the structure for that case. Then we are going to, of course, we're going to work with the loads, the dead loads, and the imposed loads, in this case. After that, we are going to translate, or maybe to factor these loads. We're going to factor these loads using our limit states of design. So we're going to have a serviceability limit state and ultimate limit state of design. After that, we're going to translate the loads into internal effects or internal forces, such as bending moments. So we're going to translate the loads into, so this is the first part. We're going to translate the loads with what we've calculated into internal effects like bending moments and shear forces. Then lastly, we're going to establish the capacity. We're going to establish the capacity of our element. The capacity of the element, not the structure. So what is the capacity? Someone may ask. The capacity is the resistance side of the structure. It is the resistance side. That is what the structure fights back with. Okay? So what the structure fights back with? It is basically what the structure fights back with against the loads that are expected to be transferred on it. The goal is to establish this inequality, that the demand, so our goal is to establish this inequality, that the demand should be less than or equal to the capacity. The demand should be less than or equal to the capacity. Then if we achieve this, we shall have had an efficient design. So let's begin our design. So well said and done. I hope you are ready with your, by the way, our design is to BS8110. So I hope you are ready with your design table, design concrete table. So let's begin with our calculations. So first things first, we're going to require the plan area of our pad footing of the base. How are we going to achieve this? We're going to use the loading. The loading here would include the dead load, which we are given as 1050 kilonewtons, and the imposed loads. Imposed loads given as 300 kilonewtons. But first, we have to work out the total dead load. How are we going to do this? The total dead load would be the GK plus the self weight. Okay? The dead load given there plus the self weight of the footing. So there's a rule of thumb. That says that the weight of concrete is typically estimated. So we have a rule of thumb here. That is the weight of concrete. The weight of concrete is typically estimated as to be 10% of the total structural load. So the weight or the self weight of concrete is estimated to be 10% of the structural load. What is the structural load in this case? We have our structural load to be 1050 plus 300 kilonewtons. So our load will be 1050 plus 300, which will give us that 1350 kilonewtons. Then we get the 10% of 1350. 10% of 1350 will give you 135 kilonewtons. So we're going to work with 135 kilonewtons as the self weight of the footing. So we can proceed. So that is the rule of thumb. So we're going to have our total dead load here as 1050 plus 135 to give you that would give you 1185 kilonewtons. Up here together up to that point. So this one here will be the total dead load. But to get the plan area, we need we're going to work with serviceability limit states. So in this case, we're going to have the loading here to be 1.0 GK plus 1.0. So our service loads in this case is going to be 1.0 by our total dead loads as 1185 plus 1.0 times 300. what do you get? You get 1185, that is plus 300. 1185 plus 300 to get 1485. 1485 kilonewtons per meter. Kilonewtons. No, kilonewtons. So that is the service loads. Then we design the plan area of the base. So our plan area of the base now can be achieved by our service loads over soil bearing capacity, which in this case is 1485 divided by soil bearing capacity was given as 170. So 1485 divided by 170, you get 8.7 square meters. So 8.7, having been told that we are supposed to design a square per footing, we're going to round it off to the nearest 9 square meters. Hence provide a 3-meter square per footing. Bracket plan area to be 9 square meter, like so. Then after that we can work out the bending reinforcement. The bending reinforcement for the footing. Bending reinforcement for the footing. How are we going to achieve this? We need the ultimate loading first. And the ultimate loading in this case, ultimate loading to BS is 110. We're going to use 1.4 GK plus 1.6 TK. So substituting there, we're going to have 1.4 by our GK, our total dead load. Our total dead load was, our dead load there was 1050 plus 1.6 KK 300. What are you getting? When you feed that into your calculators, you're going to get 1.4. So let me just do it. 1.4 by 1050 plus 1.6 by 300. So that would give you 1950 kilonewtons. That would give you 1950 kilonewtons. After that, we can work out the earth pressure. The earth pressure, Earth pressure, in this case, is the upward reaction of the soil. This one here. Okay? So earth pressure is gotten by our ultimate loading over the plan area. Plan area of base. Substitute. We're going to get 1950. We're going to have 1950 over 9 square meters. That would give you, when you feed that into your calculator, you get 217 Newton per meter square. Okay? So the earth pressure is the upward reaction of soil in that case. Then we move to maximum design moment. Maximum design moment. Maximum design moment. So design moment maximum design moment. Maximum design moment occurs at the face of the column or of the beam. I mean, of the footing. Maximum design moment occurs at the face of the footing. So it is obtained by, we'll take you back to your knowledge of theory of structures. So it's fixed, okay? The column is a fixed support. So it acts as an upside down beam. In this case, where the column here, which is this one, acts as a fixed support for the footing here, okay? Then, and the overhanging parts of the concrete bed, these parts here, this part here, now acts as the cantilever due to the weight acting, the pressure acting from the soil. So when you put it this way, it is going to be easy to understand why we are we consider it to act as a cantilever. So we're going to employ formula for calculating bending moments or on a cantilever slab, maybe beam. For this case, footing. We're going to say our PS, the soil pressure, times L squared over 2. Okay? That is the formula. So our PS was 217 times the length. The length of the face where the footing is acting as a cantilever. So that is from here to here. Then from here to that point. So that is going to be, remember the footing, the column was at 400 millimeter square column. So this part here is 400 millimeter. Okay? 400 millimeter subtracted from 3000 millimeters. That is from here to here. So that would give you 3000 minus 400. That is 2600 millimeters. Then you divide it by 2 to get 1300 millimeters. So we are working with 1300 millimeters from the column to the exterior part of the footing. So our length is going to be 1.3 squared divided by 2. So when you feed that, we're going to have let me give you the answer, 183.4. So we're going to work with 183 kilonewton meter. Okay? Kilonewton meter. Now, having worked out our maximum design moment to be 183 kilonewton meter, I think up to that point we shall have established we shall have worked out the load side, or what our footing is expected to carry. So we move to the next step, which is the capacity. Okay? So this is now what our footing fights back with. And in this case, we're going to proceed as follows. So our moment capacity. So before we proceed, we have to make some assumptions. We have to make an assumption here. So we're going to assume that the depth of our footing is 600 millimeters. Somebody might ask, why 600? So this one again is a rule of thumb. So in our scenario here, for a pad footing that is expected to carry over 1,000 kilonewtons. A pad footing that is expected to carry at least 1,350 kilonewtons. It is difficult to use 500 to 700 millimeter depth of footing, at least to avoid maybe punching failure. Okay, maybe it can also allow for constructibility, where it can accommodate the development length of the columns. So in this case, we're going to work with 600 millimeters. Then again, we're also going to assume the diameter of bars to be 20 millimeters. Okay, our bars are going to be 20 millimeters. Then we can now proceed. So 20 millimeters in both directions. So our bars are going to be 20 millimeter in diameter, running in both directions of the footing. So we can proceed with calculations for the effective depth. The effective depth, that is the distance from the top part of the footing, to have the diameter of the bending reinforcement bars. So that is going to be our effective depth. So we're going to achieve that by saying it is the overall depth minus the cover. Again, we're going to assume the cover. So our cover here is going to be 50 millimeters. Okay, since there's also going to be blinding. There's also going to be, the footing is going to be laid on top of a blinding layer. So it is 50 millimeters here is going to be suitable as a cover to our reinforcement. So effective depth, overall depth minus the cover minus diameter of bar divided by 2. So in this case, our overall depth is 600 minus our cover is 50 minus diameter of bars as 20 divided by 2. So you're going to get, that is 550 minus 10, that is 540 millimeters as your effective depth. Then we can now proceed to calculate our moment capacity, MU, which is given by the formula 0.156 FCU BD squared. So 0.156 times the concrete strength as 35 Newton per millimeter squared. So 35 newtons per millimeter squared by the breadth. The breadth, in this case, we're working with a meter by the effective depth squared. So we're going to have 540 squared. Remember, that is the values here, the units are in Newton, millimeter squared. So we can change that to kilonewton meter by multiplying it by 10 raised to the power -6. So you're going to get, so when I feed this into my calculator here, I'm going to have a value here. So I'm going to have 1592 kilonewton meter. Are you together? Up to that point, we have our ultimate moment of resistance as 1592. So you can, by inspection, you can expect that and deduce that your design moment is less than your ultimate moment of resistance, which was our goal. Remember, when we say that the demand should be at least less than or equal to the capacity. Okay? And that is what we have achieved. So up to that point, that means there is no compression, reinforcement required. So we proceed to design the bending reinforcement. Let's begin with the main steel. Our main steel formula for calculating main steel, area of main steel is M over 0.87 Fy Z. So we have the design moment, we have yield strength of steel, we don't have Z or lever arm. So let's calculate Z. Z or lever arm. Before we find the lever arm, we can also work out the stiffness factor K, which is obtained by M over HCU BD squared. So in this case, our design moment was 183 kilonewton meter. So 183 in this case kilonewton meter, we change it to Newton millimeter. So times 10 raised to the power 6 over concrete strength as 35 by the breadth 10 cube by the effective depth square 540 square. So when you feed that into your calculator, ladies and gentlemen, you're going to have a value close to 0.0179. Okay, as your stiffness factor. Then very fast, you can now have calculations for the lever arm. The lever arm Z. So the lever arm Z comes with the formula D into 0.5 D, which is the effective depth, into 0.5 plus root 0.25 minus stiffness factor K over 0.9. Okay? So you just substitute. You have the effective depth. We had our effective depth as 540 plus 0.25 minus stiffness constant of 0.179 over 0.9. Feed that into your calculator. We're going to get a value close to, ladies and gentlemen, when you feed that into your calculator, you get a value close to 529 millimeters. Okay? But remember, your lever arm Z should be less than or equal to 0.95 D. So your 0.95 D, in this case, 0.95 by 540 is 513 millimeters. So our value for lever arm here is higher than what is required. So we proceed with 513 as our lever arm. So we substitute it into our formula AS for steel reinforcement, area of steel reinforcement. So 183 times 10 raised to the power 6 divided by 0.87 times 500 by lever arm of 513. Feed that into your calculator. Feed that into your calculator and you get a value close to 820 millimeter square millimeter. Working out our steel area and finding it to be 820 square millimeters. Our BS code requires that the minimum steel area to be 0.13% of the breadth times the date square millimeter. So your minimum steel area should not be less than 780 millimeter square, which is whatever we've gotten was okay. So we move to your design table. Still from BS 8110. So we assume 20 millimeter diameter bars. So your 20 millimeter diameter bars, you are going to place them. You're going to provide H20 bars at 300 millimeter center to center. Then area of steel provided is 1050, like so. Then we're going to perform the shear check by calculating the critical shear stresses. So the critical shear stresses, the first thing you're going to do is to calculate the critical perimeter. The critical perimeter. Somebody might ask, what is the purpose of determining the critical perimeter? Well, the primary purpose, so I'm going to use this, let me draw a plan of the footing and the column. So the critical perimeter is this one. From BS 8110, the critical perimeter is at a distance of 1.5 D from column perimeter. Okay, so from here to here is 1.5D. So the critical perimeter, which is this one, the critical perimeter is obtained using the formula column perimeter plus 8 by 1.5D. Somebody is provided, the column load is provided with a wider area to prevent it from punching through the column, the footing slab. Okay, so that is the purpose of establishing the column perimeter. So let's proceed. The column perimeter at this point is 4 by 400, okay, plus 8 by 1.5 times our effective depth, which was 540. So if you feed this, ladies and gentlemen, if you feed this into your calculator, feed this information into your calculator, you are likely to get an answer which is close to 8,080 millimeters. Okay? Next, we're going to find the area within the perimeter. Area within the critical perimeter. Okay? This one here. The area inside here. How do we arrive at that? So you're going to say 400 by 3D squared. So it is the length here times the breadth here times the width here. So this one is 400. Okay? 400 plus 3D. This one is 1.5D plus 1.5D. That gives you 3D. Okay? Then you square it. So this one, you substitute it to give you square. So you feed that. You feed that into your calculator. It gives you a value close to 1, 2, 3, 4, 5, 6. That one into your calculator, it gives you a value close to 4.08 times 10 raised to power -6 millimeters squared. So the units are in millimeters squared. Okay. Then after that, you calculate the ultimate punching shear force. Okay? The ultimate punching shear force. Where does it act? It acts on the shaded region. This one here. So the ultimate punching shear force V acts on the shaded region. Okay? So the shaded region at this point, the ultimate force acting on the shaded region will be the soil, the earth pressure, which was 217 kilonewtons per meter squared, times the area of the shaded region. The area of the shaded region, which you are going to get by subtracting the total area minus the area within the critical perimeter. which is 4.08. I think the value here was in meters, in square meters. 4.08. So you feed that into your calculator, you are more likely to get, a value close to 1067.6 kilonewtons. Okay? So that is the ultimate punching shear force. Then we proceed to calculate the shear stresses. Okay? So our V is equals to V over P critical perimeter times effective depth. Okay? So the shear stress is the V, which was the ultimate punching shear force, divided by the critical perimeter times the effective depth. This point, substitute to get 1067.6 kilonewtons times 10 raised to power 3 to make it a newton, divided by the critical perimeter. The critical perimeter, which we found to be the critical perimeter, which was 80, okay, millimeters by effective depth 540. So you feed that into your calculator. This is what you are likely to get. So that is 1067.6 by 10 cube divided by 80 by 540. So your value is going to come out at 0.245 Newton per millimeter squared. Okay? Then we can calculate the design concrete shear stress. We can work out the design concrete shear stress. Okay? Design concrete shear stress from table 100 AS over BE. Okay? Our area of steel provided was 1050 divided by the breadth times the effective depth, 540. So feeding this information into your calculator gives you the concrete shear stress, the ratio. Okay, this one is a ratio of 0.194. Okay, then you move to your design table. Your design table for values of design concrete shear stress, okay, in newtons per millimeter squared. Remember, the BS code is giving you values for characteristic strength of concrete to be 425 Newton per millimeter squared. But then our design requires us to work out for 35 Newton per millimeter square. So very first, using linear interpolation, 0.194 falls between 0.15, whose value on the table, 0.15 value gives you 0.34. Okay? Then a ratio of 0.194 is what we are lacking. Then we have 0.25 giving you 0.40. So let's work out this one real quick. So we're going to have 0.25 subtracted to 0.15. That one will give you 0.25 minus 0.15, that is 0.10, giving you 0.40 minus 0.34, that is 0.06. Okay? You can confirm that one. Then we have 0.25 and 0.194 subtracted to 0.15. Okay? That one gives you 0.044. Will give you what? Okay? So you can cross multiply and say 0.44 multiplied by 0.06, okay, divided by 0.1 is likely to give you 0.0264, like so. So this value here, add it to 0.34. What do you get? You get you are going to get 0.3664, which is approximate to 0.37. So remember, this value here is the design concrete shear stress for class design concrete shear stress for characteristic strength of class 25 concrete. But then we are looking for class 35. So what do? You simply do this. Just do this. Take the class you want, divided the one we've read from the table, then find the cube root. Multiply that one with what you got, 0.37. Okay? So our VC here is going to be, you can feed that into your calculator, divided by 25, divided by 25, then multiply it by 0.37. What do you get? 0.41 as our design concrete shear stress. So the units are in Newton per millimeter square. So by inspection, what do you realize? You say, since the design, the shear stress, the design shear stress, or rather, the design shear stress V, okay, the design since the design concrete shear stress is less than V, the design shear force, then you're going to introduce that punching shear failure is unlikely to occur. Okay? Therefore, since the design concrete shear stress is less than the design shear stress, okay, then punching shear failure is unlikely to occur. Therefore, the slab depth, the footing slab depth is acceptable. Okay? And I think having performed that check would bring us to the end of today's lesson. So somebody else might ask, what if the punching shear check failed? Okay? So at this case, maybe we would have been left with two options. Okay? If the punching shear check failed at the critical perimeter that we had, we would have been left with two options. One, we would increase. So option one, increase the depth of the footing. Okay? Increasing the depth of the footing, of course, increases the critical perimeter. Okay? Increasing the depth of the footing increases the critical perimeter and definitely improves the shear capacity. Okay? So then two, we would have introduced shear reinforcement. Which is very tedious. Okay? It is very demanding to detail shear reinforcement in a slab, in a pad footing. So I think you've learned something new, and if you've not subscribed, make sure you hit the subscribe button for more educational videos, and have a nice one. Thank you.